Our Sun is a second or third generation star, formed by the remains of gas and dust from other stars that have already died. Everything that surrounds us, animals, the air we breathe, the water we drink, is composed of atoms that were created inside the stars. We are made of star stuff. This idea invites us to think that life on Earth is not an isolated phenomenon. But this idea could be incomplete. Recent scientific findings highlight an even deeper and disturbing idea. The role of the stars doesn't stop there. Not only do they create matter, the atoms that make living things, they may also be responsible for creating, evolving, and extinguishing life anywhere in the universe. But the question is, how can so distant stars be associated to our lives? What kind of cosmic link binds us to them? To search for answers, we begin a journey that will take us to some of the best research centers in the world. Here begins an adventure to discover a natural phenomenon hidden from our eyes: the cosmic radiation. An exciting world where astronomy meets particle physics and biology. In the cosmic radiation, we are looking for the link between life and the most distant stars. Perhaps stars bring more than just matter that we're made of. Perhaps we are not only star stuff. We begin our journey in southern Europe. This is the German Hispanic Astronomical Observatory at Calar Alto in the south of Spain. The dry and sunny climate of this region provides an ideal place for observing the sky. From here we can find that the stars are ovens where many of the atoms that make up living things are made. Anne is one of the scientists working in this complex.
With the help of the telescopes that we have here at Calar Alto, we can detect and investigate what the stars are made of, what elements they're composed of, and what elements are being formed in these stars.
These types of telescopes, which collect visible and infrared starlight, have been fundamental throughout the 20th century, and with their help, we know that stars do not live forever.
Stars are objects that evolve. The stars are objects that are born, have a life, and then of course they die. It will happen to our sun. It was born, has its life, now is in middle age, and within 5,000 million years will die too.
The universe is filled with regions where hydrogen and other heavier atoms in dust form accumulate. They are very special places where one of the most beautiful sky phenomena occurs: the birth of stars.
Stars are formed in clouds of dust and gas that begin to agglomerate and coalesce because of gravity. They begin to bond, and then there is a moment when this union generates such high energy and temperatures that the most elemental atoms, the hydrogen atoms, begin to merge and form more complex atoms.
The great energy inside stars allows for the creation of new and heavier atoms by nuclear fusion. Helium, carbon, oxygen, silicon, and iron are formed in gigantic stellar ovens. At the end of their lives, the stars explode as supernovae and novae. They release all those atoms into space. This stellar dust and gas is the raw material to form new stars and planetary systems.
Our star, the Sun, is not a first-generation star that was formed early in the universe. This star has been formed in an enriched media, in a medium already formed by elements that have come from other stars.
Behind these facts, a disturbing idea appears, a thought that sets us as a part of the cosmos.
The same way that the stars and other planets are formed by these elements created inside other stars, everything in this planet, all the living things, is formed by the same atoms that once were inside the stars.
We are star stuff. Life as we know it is grounded on atoms formed in stellar furnaces, but science has gone a step further. The latest findings suggest that the relationship between the stars and life in the universe is even deeper. During the death of stars, large amounts of energetic particles are also ejected into space. These tiny cosmic bullets are known as cosmic rays. Pieces of atoms are released into space at nearly the speed of light. The effects of these cosmic rays on life are disturbing, and now, for the first time, we can see a cosmic relationship which we couldn't imagine. But if we want to discover what is behind the cosmic rays, we have a serious problem. Telescopes, like those in Calar Alto, detect the light emitted by stars. Light, energy as photons, which we can also see with our own eyes. Almost all telescopes which scientists have built in the 20th century are based on the detection of photons. Some detect visible light or infrared, also at higher or lower energies, as it happens with X-rays or radio waves. But none of these advanced telescopes can help us in finding the cosmic rays that flood the universe. To detect particles passing through our atmosphere at nearly the speed of light is something quite different. We need new and advanced instruments. We need a new way of doing astronomy. In the province of Mendoza in Argentina, the international scientific community has built the largest observatory in the world for the detection of cosmic rays. The Pierre Auger Observatory, a detection instrument as extensive as 600,000 football fields in one of the flattest and isolated places in South America. From here, we will be able to discover what they are and how to hunt cosmic rays. This is a spark chamber, a device to detect charged particles. When a charge passes through the chamber, it generates rapid emission of light, which reproduces the path of the particle. Every time we see the pink spark, it means that a new particle has passed through the chamber. The particles are so energetic that they can pass through the chamber like a bullet through a piece of paper.
This is a spark chamber. What it does is every time a particle passes through it, it leaves this trail, which is a sort of spark like you see in a lightning. Actually, as the efficiency of this instrument is not very, very big, I mean, there are much more particles which is hitting us than you can see.
But no one in this lab sends particles into the camera. Moreover, no matter where on Earth we place the camera, in a desert, in a city, or in the ocean, in the equator of the planet or at the poles, the camera always detects charges.
Actually, none of us, if you want to be free of this, you may have to hide in deep tunnels. Anything, any place you are in the surface of the Earth, you'll be submitted to this radiation which is coming from outer space.
The charges that we trace with the spark chamber are cosmic rays. But despite their name, they are not light rays. Rather, they are subatomic particles, tiny bits of matter raining down from the sky at nearly the speed of light. Its enormous power allows them to reach the surface. There, they cross the rocks, water, and living things. But they are invisible. We need special equipment, like the spark chamber, to make out that they are there. Because of this invisibility, and at the same time continuous presence anywhere on the planet, the story of his discovery is worth telling. At the beginning of the 20th century, scientists opened the doors of an unknown and magical world, the internal structure of atoms. They used to chase electrons, protons, and all kinds of new subatomic particles. But in their experiments, they found something inexplicable. Ron Shellard knows this fascinating moment in history very well.
They began to realize, scientists began to realize that there was always a little awkward thing. The charge would leak slowly.
In this simple electroscope, two metal sheets are hanging from a rod. By placing an electric charge on the rod, the two sheets are separated because they have equal sign charges. The sheets' weight pushes them into their initial position, but as the charge remains, the electrical repulsion keeps them apart. However, bit by bit, and in front of the astonished eyes of scientists, the sheets started to discharge for no reason. No matter how isolated the experiment was, at the end, they ended up in the initial position. What was happening? Why was the charge disappearing?
By the beginning of the end of the 19th century, the beginning of the 20th century, scientists realized that nature had radiative materials.
Some radioactive materials emit charged particles. If the sheets were exposed to these materials, they'd end up being discharged at a faster rate.
Perhaps some stuff in the atmosphere or in the floor, in the walls, were emitting radioactivity, which is essentially charged particles. And this is what was provoking this slow leakage of charge from electrostatic objects.
The solution seemed obvious. If Earth's radioactive materials were the cause, then they just had to be separated from them. In 1911, Theodore Wolff climbed the Eiffel Tower with an improved version of the electroscopes, hoping that it wouldn't get discharged. But he got another surprise. The electroscope was discharged at a faster rate than expected. So the solution was not to get separate from possible Earth radiations. In fact, this made the problem worse. Whatever it was discharging, the electroscopes didn't come from the Earth. In 1912, an Austrian physicist made the final step. Victor Hess did one of those crazy things that characterize scientists.
And what he did was to put an electroscope in a balloon, went up. It was quite a feat because he went up to something like 5,000 meters. Going in a balloon to 5,000 meters at that time, sitting in a little basket, it's probably a little bit frightening. But, science is a little bit like that. There is always a sort of adventure associated to that.
The measures that Hess took during the rise surprised everyone.
The highest he went, I mean, the stronger it went. So it meant that whatever effect was causing that, it got even stronger as he went up more far away from the ground.
The origin of that radiation was not to be found on Earth. If they wanted to understand where those particles came from, they had to look up into the sky. Cosmic ray astronomy was born. Almost 100 years later, we are at the Pierre Auger Astronomical Observatory. But this place is very different. None of the world's biggest telescopes can observe cosmic rays, but from here, we can. Pavel, one of our scientists at the Auger Observatory, tells us why this observatory is so different.
If you want to know what is out there in the skies, you start with what you can see with your own eyes. You investigate the visible light. In the past century, we built big telescopes to investigate also the radio portion of the electromagnetic radiation, and satellites, which investigate the ultraviolet part. But if you focus only on the electromagnetic radiation, you're missing on a big part of information which is actually coming to us from the space.
To study cosmic rays, we don't analyze the light coming from space. The principle is very different. We look for particles. These particles are mostly protons, about 90% of them. From the remaining 10%, most of them are helium nuclei, and we have 1% of electrons and heavier nuclei, such as iron or nitrogen.
Based on their energy, we can roughly categorize the cosmic rays into three main categories. We have the low energy cosmic rays, which are coming from the sun, mostly because it's so close. Then we have the middle range of energies, where are cosmic rays coming from within our galaxy. And there is a good evidence that these cosmic rays are coming from supernovae, which are these massive explosions of stars. Finally, in the very, very highest energies, we believe the cosmic rays are coming from outside our galaxy. And there is a theory that actually they are coming from what we call active galactic nuclei, which are centers of the galaxies with very high star formation rate.
This is why the Pierre Auger Observatory is so different. Common telescopes in astronomy work with the light coming from space. But cosmic rays are particles, not light. They are tiny pieces of atoms that were thrown into space from different parts of the universe. Some extremely violent, such as black holes. Others nearby, like our sun. The low-energy cosmic rays coming from the sun produce one of the most beautiful phenomena on Earth.
What happens to these cosmic rays depends on how much energy they carry. If you have these low energy cosmic rays, for example those which come from the sun, they are mostly shielded by the magnetic field of the Earth. So they follow the field lines of the magnetic fields and end up in the north and south pole regions, where you can see them as the magnificent northern lights. But there is also this other kind of cosmic rays, those very high energy cosmic rays, which just go through the magnetic field and doesn't care about it at all.
If Aurora Borealis is a natural spectacle, the phenomenon that produces the highest energy cosmic rays is nothing less. But it has a peculiarity. Unfortunately, it's invisible to our eyes.
So these get into the atmosphere and hit a molecule of air. And on the interaction, it creates more particles, which are going in random direction. It's like a train collision. So before, all the cars of the train are going in a single direction. And after the collision, each car goes in a slightly different direction. So you take these particles from the interaction of the primary cosmic ray, and these particles hit other air molecules. So you have more particles and more interactions, and eventually you have this cascade of particles, trillions of them, which are going through the sky.
Thus, the difference between aurora borealis and these particle showers is the energy of the cosmic ray coming from space. The particles coming from the sun have little energy, and Earth's magnetic field deflects them towards planets' poles. There, in the upper ionosphere layers, they excite oxygen, nitrogen, and helium. When these gases return to their normal state, they emit photons, which is the light we're used to seeing in the northern lights. But Earth's magnetic field can't deviate from the most energetic particles. Cosmic rays coming from other stars reach our atmosphere at any point of the planet. There, they create a spectacular shower of millions and millions of new particles. A creation and annihilation of particles almost at the speed of light.
Most of them are absorbed by the atmosphere. Some of them, actually billions of them, reach the ground. So what you can do, you can just put the palm of your hand, and each second there are a couple particles going through it. And these are the particles we can collect with the surface detectors.
1,660 tanks like this compose the Pierre Auger surface detector, all filled with water.
This is a model of what we call the surface detector. This is the main detector. We have 1,660 of them spread all over the field.
They are arranged in an area of 50 by 60 kilometers. This is the largest observatory ever built.
An area which is much larger than the largest city in the world.
When cosmic rays reach the surface, they are hunted by the water tanks. The information they provide is later analyzed by the scientists. A single cosmic ray can generate particle showers that spread across several square kilometers, so different water tanks can detect the shower at the same time.
But it's not the only way how we can figure out that the showers are actually there. When the particles go through the atmosphere, they excite the air molecules. So you have this energy stored in the air molecule, which is later shown as a light. So if your eye was more sensitive, you could see a flash of light going through the sky, and another flash, another flash. Because our eyes are not sensitive enough, we need to use so-called fluorescence detectors, which take a movie of the sky, very, very fast movie of the sky.
Ron Shellard shows us one of the fluorescence detectors. There are 4 buildings like this in the observatory. Inside, and only by night, these instruments hunt a faint light left by cosmic rays.
Okay, we just arrived here at the fluorescent detector. Actually, it's called Los Leones. If you look at this big map, we are exactly at this point here. We have 3 other. One is Coyeco, which is on this part of the map, on the west of the area. The other one is called Los Morados, which is here on the east side of the site. And then you have Loma Amarilla, which is way out quite in the north. And this part you have all the 1,660 tanks, which makes the surface detector of the Auger Observatory.
Behind these windows, several mirrors focus light on these highly sensitive electronic eyes. they can see a small light bulb more than 30 kilometers away. The 4 fluorescence buildings watch the sky over the water tank's grid. Thus, particle showers can be studied with 2 detectors simultaneously, the surface and the fluorescence ones, reaching an extreme accuracy. That's how the world's largest cosmic ray observatory works. It pursues the clues left in the atmosphere by the most energetic particles in the universe. The astroparticle study is a very young science. It has shown us that space is flooded with cosmic rays of very different natures and energies, but also that all beings on the planet live under a constant rain of particles that were born in distant stars. We are made of star stuff, but those stars keep flooding us every second with energetic particles. Can these particles somehow affect life on Earth? Could cosmic rays be a clear link between life and the most distant stars? To search for answers, we continue our journey. To understand the deep connection between cosmic rays and life, we stop at the Astrobiology Center facilities, an associated center with the NASA Astrobiology Institute near Madrid in Spain. And here, cosmic rays will give us a major surprise. Guillermo uses this vacuum chamber to simulate the space conditions and understand how the basic blocks of life can be created. Despite his hands being here, his mind travels every day to really distant places. Places such as gas and dust clouds between stars. These clouds are huge stains in the space formed mostly by hydrogen. There are also tiny pieces of dust made of carbon and silicates.
Inside dense molecular clouds, we have hydrogen and dust. The dust is covered with an ice mantle, mainly made of water, but also of other molecules such as carbon monoxide, carbon dioxide, or ammonia.
The gas and dust accumulation prevents radiation from nearby stars from going inside the cloud. But there are some space inhabitants that can easily reach the deepest and coldest areas.
Cosmic rays are the only radiation type that can permeate into a dense or dark molecular cloud.
The cosmic rays' energy is so high that it allows them to enter into the dark and cold dense cloud's interior. It is in this place, absolutely prohibited for life, where something unexpected happens.
In that extreme environment of low temperatures, close to absolute zero, is where we have found precursor life molecules, thanks to the best radio telescopes. Among them, there are some molecules that we believe are behind the formation of amino acids and molecules related to sugars.
Cosmic rays' energy discharges over molecules and the dust-frozen surface. This creates a very rich chemistry able to synthesize the first blocks to create life.
The presence of these prebiotic molecules in space wouldn't be so relevant if there weren't a way to transport them into a habitable zone.
The cosmic rays cook complex molecules inside dense clouds. But how can these molecules reach a planet? Inside dense clouds, stars and planets get born. During the formation, the temperature is so high that none of the interesting molecules for life could survive, although there's a place where they can hide and stay for a long time.
The microscopic dust particles agglomeration in our solar nebula eventually led with time to asteroid and comet formation.
These small bodies can stay away from high temperature areas, keeping some of the molecules inside of them safe.
Radiation plays a dual role. From simple molecules such as water, ammonia, or carbon monoxide, it shapes more complex molecules. But it also has a destructive role. By having a large body similar to an asteroid or comet, only the surface is exposed to radiation, so these complex molecules have been preserved inside.
Millions of asteroids fall over already formed planets with more stable conditions. Many of them carry seeds for life within them.
In meteorites, which would be a piece of asteroid fallen to Earth, up to 100 different amino acids have been found, which represents a significant number compared to the 20 biological amino acids that make up all living things.
But science needs proof, so a space mission like no other before was created.
The Rosetta mission from the European Space Agency has been a turning point in our knowledge about comets.
After an incredible 10-year journey, Rosetta intercepted one of the comets in our solar system.
After the first grounding, which was almost at the selected point in the comet, the probe bounced and did another 2 touchdowns. But we had a stroke of luck after the first landing when a dust cloud rose and part of this dust came inside one of the instrument's tubes, the COSAC instrument.
The dust analysis that accidentally entered into the measuring instrument of Guillermo's team detected 16 organic molecules, some of them basic for life origin.
This is a universal phenomenon. Just as our solar system exists, we have discovered more than 1,000 extrasolar planets, many of them very similar to Earth. So as we receive this contribution from comets and asteroids, other planets similar to Earth could also receive them. Therefore, the starting point would be similar, and that would indicate that life is a phenomenon on a cosmic scale.
Far from Earth, among the stars, cosmic rays create essential molecules for life. But what about the cosmic rays that reach our atmosphere? Can they have any noticeable effect on life on the planet? To reveal how cosmic rays affect our atmosphere, we travel to Switzerland. Here, we meet Jasper Kirkby.
The atmosphere is crucial for life on Earth. It holds the temperature about 30 degrees warmer than if there was no atmosphere at all. That's the greenhouse gases, carbon dioxide and water. It also provides, of course, the oxygen that we breathe and the carbon dioxide that drives photosynthesis together with the sun.
The evaporated water from seas also travels through the atmosphere up to the mainland. This is where water's life cycle.
When you look at the Earth's atmosphere from space, from the space station, you see this thin blue line on the curve of the Earth, And it's a humbling experience when you realize how important that is for us to continue on Earth and how tenuous it is. It's just held down by gravity. What if it were to just disappear in a flash?
Our planet's history is full of mass extinctions, but all these extinctions had something in common. The atmosphere lost its ability to sustain life. The gases and dust released by meteor impacts or massive volcanic eruptions turned the atmosphere inhabitable.
So it's clear that the atmosphere is crucial for our life, but there's something that's behind the atmosphere that's driving it, that's causing all the processes that are important. So the sun drives processes in the atmosphere by light energy. The sun's light comes in, falls on the land or falls on the oceans and warms them up. So it warms up the land surface, and that warms up the air above it and circulates the air and transports energy and vapors from the Earth throughout the atmosphere.
For years, scientists have been finding matches between changes of solar activity and variations of Earth's climate.
So the sun is the main driver of the processes in the atmosphere. But what's interesting and what's not well understood at the moment, and is a very new line of thought, is that the distant stars, the cousins of our sun, are also, it looks like, responsible for some very important processes in the atmosphere.
And this is Jasper's research line, a new and exciting experiment to discover how distant stars affect our atmosphere. The CERN is located in the French-Swiss border. This is the home of well-known experiments such as the Large Hadron Collider, or LHC. But here, other experiments are developed as well, such as CLOUD.
So here we are in an experimental hall at CERN, next to the CERN proton synchrotron, which is behind concrete wall over there, which is a low energy accelerator, but every single proton that goes to the LHC goes through that accelerator. So it's actually one of the most important at CERN.
Under these concrete blocks, there are magnets that guide the protons to the cloud chamber. Inside this chamber, scientists simulate the composition and conditions for different atmospheres. So, this experiment allows us to see how the atmosphere behaves to the presence of ionizing particles.
Now, what you see in that silver cylinder down there is actually the thermal housing that surrounds the cloud chamber. The chamber itself, this 3-meter chamber, is inside of that, and it's a very special chamber because it's the cleanest chamber in the world. And in fact, it's the only chamber where we can do these experiments.
The chamber must remain perfectly clean inside so that the experiments can be performed with selected gas mixtures and without even minute amounts of contaminants.
Now, the importance of the particle beam is that it provides an adjustable source of cosmic rays. If you were to do these experiments in the atmosphere, you would have no control over the cosmic rays that are passing through.
It's impossible to access inside the chamber due to the need to maintain extreme cleanliness. But we can see underneath the chamber. From here, gases are added to recreate different types of atmospheres.
What you see here are a lot of valves where the gases for the cloud chamber enter the chamber itself. There are a number of different gases here: sulfur dioxide, ammonia, amines, biogenic vapors. Each of these has been identified as being precursor vapors that may lead to the formation of aerosol particles in the atmosphere, which can then grow to become the seeds for cloud droplets.
But why are the protons from the particle's accelerator reaching the mixture of gases?
It happens that if a cosmic ray goes through, it leaves a trail of ionization, and those ions help facilitate the formation of the embryonic seeds. They help stabilize these little particles. And so cosmic rays may have an effect on the formation of embryonic seeds, which then grow to become full-size seeds for cloud droplets.
This is a great finding. If cosmic rays are important for clouds formation, then they are also important for life on Earth. Clouds play a major role in shaping the long-term climate evolution of planets. This is a clear and direct way of linking cosmic rays with the conditions for life development. But we still need some more time.
We're investigating that now in cloud, and we don't have all the answers. We've seen that it does happen under certain circumstances, but we're by no means ready. We're not finished. And that's why we're doing the experiment. We still have many questions to answer.
It's too soon to say how important cosmic rays are for cloud formation. A lot of work still needs to be done. But Jasper had more to tell. There is another climactic phenomenon that is definitely linked to cosmic rays. A phenomenon that may be key to the development of complex molecules in primitive planets. A precious source of energy to form the first molecules of life.
This is connected with something called a global electrical circuit. About 100 kilometers above the Earth is the ionosphere. Cosmic rays flood rain through the atmosphere, and this causes a weak current to flow from the ionosphere down to ground. And it's purely allowed by cosmic rays.
Cosmic rays passing through our atmosphere open an electrical path in the air, which is crucial for lightning discharge.
And the really important role is played, or a really important role, by cosmic rays, because without cosmic rays, there would be much less lightning activity. So cosmic rays are very tightly connected with the global electrical circuit.
The relationship between electrical discharges in the atmosphere and life origin has been studied since the 50s with incredible results. The energy of lightning in primordial atmospheres allows the creation of complex molecules, like amino acids, from simple gases as ammonia, methane, and water. So cosmic rays, and the lightning they cause, may be responsible for creating the primordial soup of molecules that gave rise to life on our planet. We have found another way in which cosmic rays can shape and create life in the universe. But before continuing, we have time for one last coffee with Jasper.
Stars are the forges that made the atoms that we're made of, and our local star, the Sun, has provided this Goldilocks environment that has allowed us to live, has allowed water to exist on Earth, and has allowed life to flourish and people to develop. But we've learned that the stars may not have abandoned us with just making our atoms. They may have continued to look over us through cosmic rays. Out there in the Milky Way, there's a supernova exploding every 50 years or so. And this is bathing the Milky Way and our Earth with cosmic rays. And these cosmic rays have been affecting life as well, continuously, since the beginning of the Earth. They've been affecting the formation of lightning, affecting almost certainly the formation of aerosol particle seeds for clouds, and also causing a steady mutation of DNA that, once life had started, allowed the complexity of life and human beings to develop.
These words from Jasper led us to the final stop of our journey. Here we will discover another disturbing link that binds us to cosmic rays, a union point between the most violent phenomena in the universe and the genetic information that travels inside each of our cells. To help us understand this deep connection, we find Eduardo, a researcher at the Center of Astrobiology in Madrid.
Life on our planet was originated about 3,800 million years ago. During all this time, the Earth has undergone many changes that have affected the composition of gases in the atmosphere and oceans. It has also affected temperatures. There have been many variations in temperatures. And also the natural radiation levels have been affected. Despite all of this, life has been successful. Life has won and has managed to spread to virtually every corner of our planet.
But all this incredible diversity of living things have something in common, something within each cell, even in the simplest organisms, a molecule which allows the transmission from one generation to another of the information needed to create new individuals.
Inside each of the cells of this plant, there are molecules known as the DNA. These DNA molecules are used to store all genetic information, used to build a particular organism. In this case, these DNA molecules serve to generate a plant of the species Monstera deliciosa.
However, those copies, the molecular replication that is passed from one organism to the next generation, are not identical. During the process, some errors occur. Changes in the molecular structure known as mutations. They are minor changes, almost imperceptible, but these changes have allowed the vast diversity of life as we know it.
The mechanisms that are involved in DNA copying are not perfect and often introduce errors during the copy process. And then there are also external agents that are responsible to change or modify the sequence of the DNA molecule. Among these external agents are some toxic chemicals or radiation.
All living beings are exposed to natural radiation levels. Rocks and minerals contain small traces of potassium, uranium, thorium, and other radioactive elements. But it is not the only natural source of radiation to which we are exposed that can alter our genetic code.
In the past, our planet may have been affected by much higher doses of cosmic radiation, possibly because of the explosion of a nearby supernova or some other events that happened in the sun. Cosmic radiation that occurred in the past possibly performed a very important role, increasing mutations in living organisms of that time, and somehow accelerated the evolutionary process. We cannot rule out that the current cosmic radiation that exists today, even at lower doses, could also have some effect on the rate of mutation of living organisms. Obviously, there is a clear link between what happens in the stars and how life has been modeled on our planet, or even elsewhere where there may be similar life forms.
So far, scientific studies have not been conducted to show the level of importance the cosmic radiation has on the evolution of living beings. Only now we have the tools to do so.
It has some complexity. We need to study many generations of individuals to see the mutation rate in conditions in which there is a total absence of cosmic radiation, and then compare it to normal conditions with the cosmic radiation dose that exists on Earth right now.
This is a new and exciting research field that promises disturbing results for the coming years. Modern techniques of DNA sequencing and the relentless advance in the knowledge of cosmic radiation are the tools that new researchers need to demonstrate the deep bond between the stars and life in the universe. Here ends our journey. Following the trail of the most energetic particles in the universe, we have found that inside cold molecular clouds, or in the atmosphere of our planet, or even in the depths of our molecular structure as living beings, cosmic rays bind us with the most violent and beautiful processes occurring in the universe. The stars produce the atoms from which we are made, but they did not stop there. Every time a star dies, it floods the space with energy particles traveling for millions of years, arousing the spark of life anywhere in the universe.